Okay, now thank you for inviting me. And I have been waking up at 3 a.m. to catch a great conference. Today, I'm going to share with you a little bit on a study we have been doing for the last almost 15 years on a platelet, platelet modeling. And now I add a little bit on a accurate and fast to the multiscale modeling of platelet. And this is work jointly with people in our medical school at Stony Brook University and people in applied mathematics and as well as the IBM team. And the view, I have a little animation, but that's okay. So I have a little overview of the presentation with a couple of W's, what we do, why we do, and how we do. And the first one is what we do, basically is to reveal the mechanism of a platelet activation and aggregation under stimuli. And obviously, why we do this, and it will be clear in a few minutes, but I will give that out now, is indeed a problem of matter of life and death. And intellectually could be the first understanding of a platelet mathematically. And of course, for practical purposes, it's a better healthcare and artificial organs, drugs, and personalized medicine. And how we do it, and this is the whole presentation. And we developed, integrated a multi-scale a framework. In this framework, we implemented in a package we called IPDyna by using these basic platelet properties and discretization or modeling parameters, basically using AI or artificial intelligence machine learning to figure out those basic parameters. As I mentioned, a platelet everyone has, and blood. And a platelet is a very tiny, little thin, almost like a little cookie on the middle left of my screen. And the size is a couple of microns in size, a typical cell. And it's just like a frisbee or cookie. And this little cookie has about 1 trillion atoms. And this 1 trillion atom is very hard to simulate if we consider using even supercomputers from atomic level. So we have to design models to enable this. And a typical platelet generated from bone marrow, I don't know if you can see my pointer, from bone marrow has a typical lifetime of a week to 10 days. During those approximately a week long, the platelet does fantastic job to sustain or support life, and it can actually destroy life if it doesn't do the right thing. And in academic or the latest research over the last almost a decade is to study, I always call triple A's. And 1A is adhesion, basically how the platelets get absorbed to certain membranes. And a second one is the activation. Normally, I would say activation first. A platelet, like the cookie I mentioned before, will magically grow a dozen to about a dozen spikes. And those spikes enable them to connect. And this connection is what we call aggregation. So our study is focusing on those triple A's. And you stimulate a platelet, and a platelet will activate. And they activate, they had two possibilities. One is to aggregate, another one is to adhere to membranes. So this is the a model. In this, we had a little animation. Unfortunately, the PDF didn't collect the a particular one. And this is a vessel on the left upright corner of the upper right half of the screen. Is the a vessel platelet flying in and out of your along the vessels. And there are a couple of states. Obviously, it's a quiescent state. That's when platelets are doing their job. 99.99% of them are doing this. Occasionally, they get activated. After they get activated to do fantastic things. And this activation principle mechanism is unclear. If you look, this is a microscope picture on the lower left corner. And the picture on the left of the lower left corner is the so-called resting or quiescent platelet to look really good. And on the right is the activated platelets. And you may actually get a little bit annoyed for almost 5 minutes. I still haven't mentioned supercomputing yet. And we will get there very soon. But those platelets, they do things in our blood for better and for worse. And they are really doing interesting things. And this one is another a picture of illustrating the platelet aggregation. On the right is really a clot, and I'm going to explain what that means. And the thrombosis, many of you who are not in medicine may not know exactly what that means. And this on the left is a normal heart. On the right is a damaged or is a heart with a plaque built up. And this built up plaquette will narrow the arteries. And how they narrow artery, sorry, and with the damaged heart or with the narrowed arteries, and the platelet will have to pass through a narrow channel. And this narrow channel will cause higher pressure, and this high pressure will cause activation. Activation will cause aggregation. So we use supercomputers to build models to understand the entire process. As I mentioned, this heart attack obviously is a result of a clotting mostly, and then the stroke, besides hemorrhage, is the clotting for causing strokes. And there's a little statistics, by the way. This one is about 10 millimeter clotting on the right of my screen or your screen. You can see the this is extracted from a patient, obviously the deceased patient with this huge clot. And if you see here is very heavy, and the approximately almost 38 million people got affected by the clotting worldwide. And 38 million people, you can actually check certain countries. I know Canada's population is about this number. And the worldwide, the number we had is 31%, almost 18 million deaths as a result of a clotting in 2012. The number is actually getting up instead of down. And now from a US number, as you can see, 300K, almost a third of a million, had clotting, and 600 million, 300 million deaths. And there's about more than double that on a non-fatal clot. You can see the importance at the beginning. I said life or death. This is what I meant by that term. You know, the aggregation or clotting is not always bad. It's actually good. Sometimes you need it, you want it. in upper left corner, as you can see, if you get a cut and without the platelet activation to cause stopping, then the blood will just flow out, gushing out without stopping. That's serious. Sometimes you may actually say, okay, I'm going to use a way to block it. It's not easy to do, obviously. And for this upper left corner picture, but for this internal bleeding, that happens to a lot of people who take an aspirin, and they cannot stop internal bleeding. And those internal bleeding is fatal in many situations. And now here comes the modeling part and mathematical model. And platelet, as I said, has approximately 1 trillion atoms. If you simulate 1 trillion atoms, so the community we are addressing now is capable of simulating large things, but 1 trillion atoms is not possible. How do we handle this? We just have to scale this to make a multi-scale. And this picture basically illustrates the scales of the a problem. As you can see, let me show you the lower right corner, like a satellite picture. And this literally is a platelet model we built, and with a little core inside, and then others, and then let's go to different scales. We have multiple methods to simulate all the way down to the cytoskeleton modeling. We use the actual atomic or molecular dynamics, and we go on to a coarse graining MD. And coarse graining MD, I'm going to explain this a little bit later. You basically aggregate approximately a few hundreds to 1,000 particles or atoms together to form an effective particle. And then you use a CGMD to simulate those. And then get an even higher level, we use a dissipated particle dynamics all the way to make things much simpler to simulate. And this is a more detailed illustration of the multi-modeling model for different parts of the simulation. Let me get a little bit faster since I wasted a little time at the beginning. Now the multi-scale modeling, as you know, is everywhere. It turns out multi-scale is everywhere in science. And you don't want to simulate a multi-scale problem using a single scale. Single scale, if you go to the larger scale, you simulate, you miss the fine structure. If you go to the fine scale or detailed scale, you wasted time for the larger scale. You say, okay, I stay in the middle. You miss both. So this is a picture showing in nature, you can get to the size of an electron, something like 10 to minus 16 in size, unit meter, to the galaxies, something 26, 1025. As you can see, you got almost 50 decades. This is a terrible scale to deal with. Now we get to a scale we are dealing with here is from atomic to organ. As I just mentioned, as electron nobody can simulate, just inside a cell, or even probably inside a large molecule. So we need to go from electron to molecule all the way to cells. This is red blood cell I'm showing, and then to organ. And this is also a multi-scale problem. You need to scale the problem in greater details. So we have a large number of graduate students. So I said each picture is a PhD thesis. So we try to survive with learning. And this one here, a classified problem according to the number of platelets and according to how they interact. There's one physicist like this kind of work, and American, I'm sure can see some a resemblance in physics. And now we study a single platelet and how they flow or flip in the blood stream. And then we see on single platelet, how they activate in the flow, and then how the a single platelet, how they get attached or get absorbed to the wall. So this is a one class of a problem. We have a PhD for the activation 2 or 3 years ago, and now we have a bunch. Each one is almost assigned as a thesis. And now there's a flow, a free flow. The second one is a two platelet. Two platelet. You study first the aggregation, and then there's a so-called recruitment aggregation. Recruitment meaning there's a platelet already standing or get absorbed to a wall, and how that's going to attract other platelets. Typically, when you get a cut, depending obviously how big the cut is, you need to have something like 1 million platelets to get recruited, and they actually happen with a sub-second is magically coming together. And obviously, when you have more platelets, surprise, surprise, from 2 to 3 is a non-trivial change computationally and scientifically. And so 3 platelets, I have exactly the same stories here. And then there is some microscopic on the right side. There's 2 pictures to show the physiological interpretation, what I just mentioned. And now grab a pointer by clicking the arrow on it. Okay, let me see which one is that. By clicking on part of the clicking white window pointer, let me see if I can find a pointer. This will be probably a pointer. Oh, now it's back. Now I lost my screen. Oh, how do I get back? Let me do. Oh. Okay, now the screen is back, and this very busy slide, and this slide is terribly busy, and a American Eye get together because of this picture some almost almost 10 years ago. And this picture basically is the so-called multiscale upper right, upper left. Picture is illustrating how we couple different scales and what physiological components we simulate and what equations we describe the forces of the interaction. As you can see, we go all the way down to the lower left corner of this space and time a Cartesian coordinate. And the red one here is the MD and all the way to CFD. And we must have people in the audience, experts in CFD. So we went through multiple scales, namely in space, we went through 6, and in time, we went 9 time scales. And it's a nightmare in terms of simulation. And now I'm going to show you how we use machine learning or AI to carry out those calculations. Some of the talk of this part, I'm going to be a little fast, and since you have the a PDF there, if you're interested, or we can talk offline. And in this, we use our package called IPDyna to address the problem using AI in 3 aspects. The first one is an inverse problem to find elementary parameters. The force laws have to be implemented in this particular case of platelet, and we need to discover the parameters. Is a massive inverse problem. Parallel computing here plays a major role. So, of course, AI as well. The second one is the extracting the structural properties from in virtual experiment results from the video, we actually collect our graduate students' platelets they donated, and we use those. And of course, we have to go through all sorts of laws to be able to use. And we have a video to see the flowing of a platelet in the microchannels. We have videos for approximately 1,000 frames per second. So it's a millisecond time resolution, and sub-micron size in terms of pixels. And the last one, and it's probably more relevant in computing people, is how to make necessary computing without losing accuracy. So this, the machine learning plays a major role on this. Okay, now the first one discovered the fourth law, and this picture looks pretty simple. Took our students almost 2 years to get. And what do we do here? And the force field for the calculation for the CGMD portion, we have two very simple terms. One is the Moore's law, not the this is Morse, M-O-R-S-E, and it's in solid state physics is pretty popular. And we introduced the fourth law to study the blood plasma. Actually, not plasma, is the gel inside the platelet. And then the second term in the fourth law is the Hooke's law. Basically, is the force of a rubber band in our interaction of the entire gel with the cytoskeleton of the platelet. And okay, this is good, but it's not good. There are many parameters we don't know. We don't know what Rij is, and we don't know what R naught is. We don't know what Fa is. We don't know what D naught is. A bunch of, Rij we do know. We have to calculate those. And those parameters we have to figure out by machine learning. And it's a massive computing problem because you need to perform a lot of calculations to enable you to match with laboratory experiments. And it's a classic inverse problem. I believe this is one of the major calculation problem. And the way to do that basically is the optimization problem here. And you need to get the argument of the in silico. This in silico is a calculation, and the in virtual is our wet lab, if you may. And and we use an L2 norm. Actually, we could use many different norms. And in this optimization, you need to perform whenever you have a ground truth. That is the laboratory experiment. You need to perform a lot of calculations, and those are the each one takes a day or two MD calculations to figure out those parameters for you to do calculations in the future. If some of the people in the audience remembered how to do protein study, you need to have the force field determined. And in order to determine the force field, you need to determine the parameters. That's what we did for this portion of the simulation. And naturally, this is just a little schematics for the procedure, how to perform the inverse problem for determining the parameters. And this is one example of setting up our calculation for a recruitment aggregation, recruiting aggregation. And I just wanted to demonstrate using our parameters, we actually get correct result relative to the experimental results. So that is the ground truth we have to respect. And second one is we developed a learning system. This is the PhD thesis of one student on segmenting the platelet from experimental results. If you say, okay, I got those lab images, and now go ahead with the calculation. that's not that easy. We have to get geometrical and physiological parameters from the platelets, and then we have to use the AI to determine for example, the segmentation part. And this is procedure for this portion. There's 5 or 6 steps. And the first is there was a picture I actually changed it to words, make it quicker. And it's a blood extraction, and then it's isolation of platelets. Blood has almost 10 different components. You need to extract the platelets, and then you do an image. Remember, this is just imaging. And then you have to do a little bit on a processing, and then finally you need to extract the properties. And this number 5, number 6 are the major work what we did for extracting the properties. And properties, as I said, is a geometrical as well as a physiological properties from this portion of the MD. This is more or less a picture. Unfortunately, this is an animation. You can see how the platelet actually fly in inside. You need to have this segmentation done. This is lower right, two slides, and they are the microchannels. We took a slice of the picture, and go into lower left corner of the picture is building the geometrical properties. And of course, this is a very expensive operation. You get the properties, you save in a database from which you build future studies. So this is what we did. And this one is actually another animation. The real picture we took from our wet lab to see how platelet get aggregated under different shear stresses. And as you can see, the lower left picture is a big blob of platelets, and upper right picture, and it's just getting building up of those platelets. And we'll see how they actually get aggregated. You know, the aggregation is not permanent. They get, obviously, they get attached, and then they actually, because of the flow, they can actually fly away, depending on the strength of the flow. So then sometimes people may even almost get a heart attack. Some magical event will get this clot dissolved. So that can happen. Now this is picture. What time I should finish? 45, 30. I'm not supposed to finish almost now. This is a picture to show you all those different bizarre pictures of platelets. And there's one is activated and get this serial paths, and then there's resting platelets, and then there's a tether, and those are the platelets in bizarre shapes. We have to use machine learning to detect them. And as I mentioned earlier, this is high resolution, high speed in this area in a physiological lab. We can collect almost 2 billion images within half an hour, and processing those 2 million images using a human being is almost impossible. If you can get one, a graduate student may take an hour to get one picture. Thinking about 2 million, so that's 2 million hours. Nobody can do. As a matter of fact, before we discover this a learning system, people actually survive using undergraduate students to detect those images. Obviously, it's slow and inaccurate, and our method is changing this completely by this learning system we discovered, and we are completing a paper on this. If you're interested, we'll discuss with you, probably offline. And the learning is divided into 2 major systems, major portions, and then a minor one. And this one is this multi-agent network, and then this next one is a policy network, and then finally we have a little reward network. I'm not even sure if the last word is correct, or reward. And it's a final, this somewhat a control to when you get a result, you need to get one more time to screen it. And this is the result. Let me this is actually an animation, and this is the result compared to the existing methods relative to ours, and our method are much better than the existing methods in terms of getting the images of platelets. As you can see, interestingly, I keep telling my Chinese students to use different color schemes. The left one, if you see the picture in this 2D condition on the left, there's a green bar. That's bad, and the force rate is high. And those little ones here below is almost a 20th of that green bar are our results. So we amplified it, and on the average, we are 20 times better than the published results thus far. And so that's the improvement. And this one here is interesting. And with machine learning, which is much faster than the massive MD calculations. And I was actually a little bit generous saying it takes a day, usually takes a week for one complete experiment for one data points. We actually become lazy and remove a couple of experiments when in the parameter space, and others will be done by machine learning. As you can see, we're getting pretty close on that. And now the third one, I will finish in less than 2 minutes, and is how to speed up the calculation. As you know, most of our calculations take weeks and months for one set of data points, one set of data to get one data point in a physiological space. So it's not practical. Not only is not practical, it's very wasteful in the older calculations. So we use adaptive time stepping for the MD, the integration of forces. This one we speed things up by thousands of times in two aspects. Today I concentrate on the time dimension. In spatial dimension, you go to the right components to perform using the right spatial scales. That by itself is a big separate talk. I only concentrate on time direction for the integration. We basically eliminate unnecessary calculations without sacrificing the accuracy of the calculation. And this one here, the little guesstimate I did on back of the envelope estimate, and the calculation using, if we use all, just look at the 33 years result in a typical simulation, we get honestly using fastest computer we have today. By the way, we have access to that one on a summit, IBM, and this calculation takes approximately 33 years. Nobody can wait for that long for PhD. And well, obviously, people will say, I'll use CFD to do that. Well, with all respect, CFD is not going to give you any useful results alone. And we just need to have to use more detailed. This one I will just skip, and is showing this one I also skip, and it's a multi-time step in how to perform integration. And this one I will, there is one spatial integration, and I will also skip this one. And let me get to the almost the last picture. And this is on our crown jewel in speeding up the calculation. And the calculation, I mentioned thousands of times, this one is a portion of it, a much smaller portion of it, okay? So the online learning with let me go as quickly. And this is, we collect the physical states of the simulation, and using the physical states of the past, recent past, we project the future time step sizes. So it looks like you look at rear mirror to drive forward, but it's not. Physics here or physiology here is more continuous than this random road curving. So we look at the back and project the future. And we build a learning system is rather elaborate. And then we use the projected resolution for the future, for the near future, for how many steps we use this new time stepping. And we manage to survive the calculation within. You do the lowest and the finest calculation as the ground truth, as the basis, and you compare with that. We lost merely 3% on accuracy, and we managed to speed up the calculation by almost 50%. So the machine learning here, or the AI portion, by looking at the back and you eliminate unnecessary calculations. Now I'm going to finish 1 minute, less than 1 minute. This is it. And conclusion, and we'll questions.
Hello, YUEFAN.
Yes,
Thank
I'm
you
done.
very much for a great talk. Of course, it's dense with information. It's so much work over years and years of so many of your students and collected results. Could you tell us, will you be sharing your slides with the
Actually, Marek, I have a much bigger slide. I took probably on 1/4 of it,
Yes.
and that was a PPT. I will. So then you'll notice the presentation is a little jumpy.
Yeah.
I took a longer seminar. I will prepare
Thank
a. In fact, there's a sharing folder. I may even load up the latest papers.
Thank you. So we will make it available through our conference website, because there were certain slides which appear to be technical, but they are extremely interesting. And even this slide on the time scales and the way how you adjust the time steps, that was very, very interesting.
Yes, we are completing the paper. I was supposed to be finished today for submission.
Now, do we have questions from the audience? We may take 1 or 2 questions. Are you planning to simulate the effects of various thrombolytic drugs on blood clots?
Wow, my gosh. There is one portion of our simulation can be easily adapted to for the corona virus absorbing to the surface of other membranes, and could easily adapt to that. Unfortunately, we are busy with the current project completion. Could this whole methodology can be reasonably easily generalized to other similar simulations? We are struggling with the IPDyna package to enable people to use more automatically.
Perhaps I will ask a question, YUEFAN. From your simulations, would you be able to indicate what are the critical factors which might make a person prone to clotting or to sort of unhealthy conditions?
That is a 30 million life question. At this point, we didn't know. We still don't know. There is one, surprisingly, we just started a project to analyze the baby's platelets. You never see a baby having a heart attack or very young kids. So the younger platelet from platelets are the same, about 7 days of life. Even when 100 years old, we still have platelets of that age, but they get more damaged as we of the activation. And we still don't know. We tried to understand if high pressure will be the is the cause. It's supposed to be the cause, but our laboratory experiment didn't suggest anything. We need to make it 10 times higher in the lab to cause activation.
Right. YUEFAN, I'm sorry, we have to finish your allocated time slot, close it.
Thank you. Sorry to
thank you
take,
so much. And for all participants, YUEFAN is speaking from Stony Brook.